Hello and welcome, dear students. In today's lecture, we will discuss ocean temperature, its meaning, and the major factors that control its variation. Ocean temperature refers to the heat content of the oceanic water at different depths. Ocean temperature affects marine life, drives ocean currents, and influences coastal ecosystems. The sun is the main source of heat, but many factors like atmospheric conditions, the angle at which the rays of the sun hit the oceanic water, length of the day, Earth's distance from the sun, and the latitude play a role. Owing to the constant movement of ocean waters both horizontally and vertically, the heating and cooling mechanism of ocean is quite different from land. This dynamic nature of the oceans makes the understanding of ocean temperature and the factors governing its spatial and temporal variations both important and scientifically fascinating. This dynamic nature of oceans makes the understanding of ocean temperature and the factors governing its spatial and temporal variations both important and scientifically fascinating. With this background in mind, we will now examine the measurement of ocean temperature and its vertical layering in the oceans. The temperature of the surface waters of the oceans is measured using high accuracy standard type of thermometers such as conductivity temperature depth thermistor, and the subsurface temperature is measured using a reversing thermometer like protected reversing thermometer. Based on vertical temperature variations in the tropics, the oceans can be divided into three layers, namely the warm topmost layer of the ocean is almost 500 meters thick and is present in tropics throughout the year. In this layer, the temperature ranges between 20 degree to 25 degrees Celsius. This temperature range is also observed in the mid-latitudes during the summer. The second layer, known as thermocline, is characterized by rapidly changing temperature with depth. This layer, just below the topmost layer, is deep in the tropics, greater than 500 meters, and becomes shallower as we move towards the poles. Then sea layer, that means the third layer lies below the second layer and is very cold, extending all the way down to the seabed. Owing to the presence of cold conditions, the first two layers are absent in the polar regions and only the third cold layer is present. Now we will examine the daily range of temperature. The change between the minimum and maximum temperature recorded over a 24-hour period is called a diurnal, or we can say daily range of temperature. In the oceans, the daily temperature range is very minimal with only a difference of 1 degree Celsius between minimum and maximum temperature. The minimum temperature is measured early in the morning at 5 a.m. and maximum temperature 2 p.m. during the day. In high latitudes, the diurnal temperature range is 0 to 0.3 degrees Celsius. And in low latitudes, it is approximately 0.3 degrees Celsius. There are various factors that influence the daily temperature range, such as atmospheric conditions, stratification of ocean water, and stability and instability of the air masses. For example, under clear skies, the ocean waters heat and cool rapidly, making the daily temperature range little bit higher than observed under overcast conditions. Similarly, stratification inhibits maximum heat transfer through conduction, making the daily temperature range very low. Next, let us explore the yearly temperature range. In the northern hemisphere, the yearly temperature range, that is the maximum and minimum temperature, is measured in the coldest and warmest months of February and August respectively. Likewise, in the southern hemisphere, the yearly temperature range is measured in the coldest month, that is July, and warmest month, that is January respectively. The average yearly ocean temperature in the northern hemisphere is 12 degrees Celsius, while as it can range from freezing point at Antarctica to 30 degrees Celsius near the equator in the southern hemisphere. Nevertheless, regional conditions like nature, location and size of the sea, prevailing winds and variation in the insulation influences this range. For example, oceans with bigger size such as Pacific Ocean has lower range of yearly temperature, while as smaller oceans like Atlantic have higher range of yearly temperature. Now, having understood the daily and yearly temperature ranges, we now examine the major factors that shape temperature trends in oceans. The distribution of ocean temperature is studied in two ways, horizontal and vertical, and is influenced by several factors including latitudes, difference in the angle at which the rays of the sun strike the ocean waters are the main causes of sea surface temperature variation from low to high latitudes. In the higher latitudes, the rays of the sun are slanting, which cause more reflection than absorption of the solar radiation, making ocean waters little cold. However, in the lower latitudes, due to more vertical impact of solar insulation, the oceans become warm very fast. It is good to mention here that between latitudes 40 degree north and 40 degree south, the temperature of the air is generally higher than that of the water, and it decreases towards the polar regions in both the hemispheres. Apart from latitudes, the uneven distribution of land and water between the hemispheres also plays an important role in shaping ocean temperature patterns. Ocean water temperature varies between the northern and southern hemispheres due to the greater extent of land in the northern hemisphere and the dominance of oceans in the southern hemisphere. Owing to the greater extent of land in the northern hemisphere, which heats up quickly, additional heat is transferred to the adjacent oceans, making them warmer than those of the southern hemisphere. Isotherms in the northern hemisphere are irregular and deviate from latitudes because of contrasting warm and cold land areas. In contrast, the dominance of oceans in the southern hemisphere causes isotherms to follow closely the latitudes. Land enclosed seas in the low latitudes are warmer due to strong heat input from the adjacent land masses compared to the open oceans. For example, at the equator, the yearly range of ocean water temperature is relatively low, that is 26.7 degrees Celsius, compared to about 34.4 degrees Celsius in the Persian Gulf and 37.8 degrees Celsius in the Red Sea. The effect of land water distribution is further modified by prevailing wind systems. We know the earth is marked by various prevailing wind systems, trade winds, westerlies and polar easterlies. The trade winds blow from northeast and southeast in the northern and southern hemispheres respectively. Similarly, westerlies blow from northwest in the northern hemisphere and southwest in the southern hemisphere. Likewise, polar easterlies blow from east to west in the northern hemisphere and west to east in the southern hemisphere. The movement of these prevailing winds is influenced by the rotation of the earth, Coriolis effect, along with the spatial distribution of pressure belts across the surface of the earth. Wind direction from land to sea or from sea to land influences the process of upwelling or downwelling of the ocean waters, thereby influencing the temperature distribution of oceans. For example, offshore winds moving from land to sea cause upwelling of the deep cold water. This cold water replaces the warm water at the surface at place of upwelling, leading to longitudinal difference in surface sea temperature. In contrast, where the prevailing winds move towards the shore, especially in lower latitudes, the water piles up near the shore, causing downwelling of warm water, thereby raising the temperature at the downwelling locations. Similarly, where the two wind systems move away from each other, they cause upwelling of the coastal water, while as where they come close to each other, the warm water piles up, causing ocean downwelling, resulting in higher ocean water temperatures. For illustration, trade winds in the tropics between 30° north latitude and 30° south latitude cause cooling of the eastern ocean margins due to surface water deflection and cold water upwelling. Concurrently, the water piles up along the western ocean margins, resulting in warmer temperatures and downwelling. Likewise, in the middle latitudes, prevailing westerlies cause upwelling and cooling along the western margins compared to the eastern margins, which are warmer due to downwelling. Prevailing winds not only influence surface temperature directly, but also set ocean waters in motion, generating surface currents. Based on their region of origin, these currents can be warm or cold. The warm currents raise the temperature along their paths, while as cold currents bring the temperature down. For example, Gulf Stream. It is a western boundary current in the Atlantic Ocean and is propelled by trade winds north of the equator. Owing to high water temperature at these locations, the Gulf Stream acts as a warm current, increasing temperature along the west ocean margins. As it passes through the eastern coast of North America and western coast of Europe, it raises the temperature above what is normally expected at these latitudes. While as Canary Current, it is a cold current that moves from higher latitudes to lower latitudes towards the equator along the eastern margin of the oceans, thereby cooling the western side of the continents. These coastal regions are much cooler than their corresponding coast on the western side of the oceans because the latter is influenced by warm western boundary currents. Besides the above major factors, some minor factors like regional weather conditions such as cyclones, storms, cloudiness, foggy conditions, evaporation, precipitation, presence or absence of submarine spreading centers, shape and location of the sea also influences sea surface temperature. For example, longitudinally extensive seas at low latitudes are warmer than seas that are elongated latitudinally. Mediterranean Sea records higher temperature than the Gulf of California. Similarly, the nature of the sea, whether open or closed, also affects the sea's surface temperature. Enclosed sea at low latitudes records comparatively higher temperature than the open seas. Conversely, in higher latitudes, open oceans are warmer than closed seas. For instance, Baltic Sea has temperatures near 0 degree, while as nearby open oceans record 4.4 degrees Celsius. Now, having discussed the major and minor factors influencing temperature, we will now examine how temperature actually varies across the ocean surface. The temperature on the ocean surface on an average is 26.7 degrees Celsius, and the highest temperature is recorded not exactly at the equator but slightly north of it, that is 5 degree north latitude. The temperature steadily decreases towards the poles from the equator. The lowest temperature is documented from 80 degree north latitude to the North Pole and from 75 degree south latitude at the South Pole. The temperature decreases at an average rate of 0.5 degree Celsius per degree of latitude from lower to higher latitudes. The average sea surface temperature at 20 degree latitude is 22 degrees Celsius. At 40 degree latitudes, it is 14 degrees Celsius, and at or near the poles, it is 0 degrees Celsius. In the northern hemisphere, the oceans record comparatively higher average temperature than the oceans in the southern hemisphere. Although 17.2 degrees Celsius is the annual average temperature of all the oceans, but in terms of hemisphere, northern hemisphere has higher average temperature, that is 19.4 degrees Celsius per year, than the southern hemisphere, which records 16.1 degrees Celsius annually. As we discussed earlier, this variation in the annual average temperature in both the hemispheres is because of the uneven distribution of water and land. With respect to the world oceans like Atlantic, the Pacific, the temperature also shows variation. For example, the temperature decrease in the Atlantic Ocean with an increase in latitude is very low due to warm ocean currents. Between latitudes 50 to 70 degree north, the recorded average temperature is 5 degrees Celsius. This decreasing trend of temperature from equator to the poles is more distinct in the southern Atlantic. The Indian Ocean is one of the warmest oceans, with tropical regions of Bay of Bengal often exceeding 28 to 30 degrees Celsius at the surface during summer months. However, the average ocean temperatures are around 25 degrees Celsius. Similarly, the surface ocean temperature of the Pacific Ocean also reaches above 30 degrees Celsius in the western tropical Pacific warm pool, with surface water generally remaining warmer than at higher latitudes. The maximum short-term temperature may reach up to 32 degrees Celsius. Semi-enclosed seas such as the Persian Gulf and Red Sea regularly record some of the highest sea surface temperature globally, often reaching more than 30 degrees Celsius. Near polar region, surface water approaches near freezing point temperature, that is 0 to 3 degrees Celsius. The surface water temperature of the oceans being higher gives off heat to the cold air above. For example, between latitudes 20 degree north and 55 degrees south, the air temperature at a height of 8 meters is 0.8 degrees Celsius, cooler than the ocean temperature in the Atlantic Ocean. This air-sea temperature difference influences atmospheric stability and plays an important role in driving ocean-atmosphere interactions, particularly the generation of winds, which in turn control ocean waves and currents. A lot of seasonal variations occur in the heat emitted by the oceans during summer as well as winter, which causes fluctuations of temperature over the continents and the oceans, especially during winter season. The temperature difference between sea surface and the air leads to the formation of foggy conditions over the oceans. This happens because the air is cooled by the cold sea water, triggering fog formation. During the spring and early summer, sea fogs form frequently, particularly in the high latitudes. As the air coming from the land is warmer than the sea, while surface temperature mainly varies with latitude, temperature also changes with depth. Let us see how. The temperature at the surface of the oceans is maximum because of the reception of the solar rays, and they efficiently penetrate up to 20 meters and seldom penetrate beyond 200 meters. The heat is then transferred to the lower layers of the ocean through conduction. Thus, the temperature decreases towards the ocean depths from the surface. The decrease in the temperature with depth is very rapid, up to 200 meters. Below it, the rate of temperature decrease slows down. From this perspective, the oceans are divided into two zones. Photic or euphotic zone, it is the upper zone which receives solar radiations reaching up to a depth of 200 meters. This is followed by aphotic zone, which extends up to the bottom from the base of photic zone. The solar radiation does not penetrate up to this zone. The salient features pertaining to the vertical temperature distribution of ocean waters are discussed. Although there is a decrease in the seawater temperature with depth, but the rate at which temperature decrease is not uniform. Below the depth of almost 2000 meters, the temperature change is negligible. The rate at which temperature decreases from equator to poles is not uniform. Although there is a decrease in ocean surface temperature from equator towards the poles, but the temperature of the ocean bottom waters remains uniform. Nevertheless, the rate of decrease in temperature with increase in depth at or near the equator is fast as compared to towards the poles. The exciting observations of German Antarctic expedition in 1911 suggested the sea surface temperature at 40° north latitude equals the temperature at the depth of 100 meters at 7.3° north latitude. Similarly, the sea surface temperature at 50° north latitude is the same at 200 meter depth at 7.30 north latitude. The sea surface temperature at 60° north latitude is same as at the depth of 700 to 800 meters at 7.3° north latitude. In regions of upwelling, even though located in warm regions, record low temperature at the surface. In these regions, the rate of decrease in temperature with depth becomes very low. Conversely, areas of downwelling have comparatively high sea surface temperature and the rate of temperature decrease with depth is rapid. Some seas record high temperature at greater depths, for example, Sargasso Sea, Mediterranean Sea, Red Sea, Solo Sea, etc. For example, in the Mediterranean Sea, the temperature at the depth of 1829 meters is 24.4° Celsius. However, at the same depth in the Indian Ocean, the temperature is only 1.1° Celsius. Such strange conditions are observed at low latitudes in the seas that are enclosed. In higher latitudes, the surface temperature in enclosed seas is lower than the temperature below. This phenomenon is known as inversion of temperature. There is a well-defined vertical thermal layering of the ocean water in the lower and middle latitudes, based on which the oceans are divided into three layers. The top layer is the warm water mass having a thickness of 500 meters. The average temperature in this layer ranges from 20° Celsius to 25° Celsius. This warm layer exists throughout the year in tropics but develops only during summer season in middle latitudes. Just below the upper layer is a transitional layer which extends from 300 meters to 1000 meters depth. This layer, known as thermocline, is characterized by a rapid change in temperature with increase in depth. The lowermost layer, starting at 1000 meter depth, extends up to the bottom of the ocean. The water of this layer is dense and cold and makes the major water mass of the ocean. In addition, summer heating creates seasonal thermoclines which occur between 40 meter and 100 meter depth. The diurnal thermoclines are also observed in shallow water occurring at a depth of 0 to 15 meters. In the polar regions, the thermocline is absent and only one layer of cold water is observed, which extends from surface to the ocean bottom. Temperature is the most important factor controlling seawater density. If the temperature is high, the density is low, and vice versa. The heating of the seawater through insulation leading to thermal expansion resulting in low density. In contrast, lower temperature results in seawater cooling, hence thermal contraction. This phenomena results in volume decrease and density increase of seawater. And it is good to mention here that the role played by temperature in controlling the density is more distinct in tropical and subtropical oceans. The importance of temperature in controlling the density of seawater decreases polewards. Thus, an equivalent change in temperature produces much greater change in density in warm low latitude regions than in cold high latitude regions, approximately 3 times greater for warm waters. It should be emphasized that cooling of seawater below its freezing point does not lead to further increase in density. As temperature approaches 0 degrees Celsius, seawater starts to freeze and ice crystals form. These crystals hold water molecules in a more open arrangement, preventing closer packing. Consequently, the number of water molecules per unit volume decreases, resulting in lower density, which explains why ice floats on water. Therefore, the density increasing effect of cooling is effective only up to 4 degrees Celsius. In polar regions where seawater temperature remains close to freezing point and show limited variation, temperature plays a relatively minor role in controlling seawater density. This is all for today's lecture. I hope you enjoyed and learned something new. Thank you for watching.